All right, guys, so 4.3 today. We're starting to get into a little bit deeper into our integral calculus. So up to this point, and I know we've talked about this in the last couple videos, but most of what we have been doing is differentiating, right? We've been taking derivatives, and that's what's kind of happening over here on the left is we're finding a point and we're looking at the tangent line to the curve at that point. That's kind of been the focus of what we've been doing, finding the slopes and the rate of change and the tangent lines. The other half of calculus is called integral calculus, and that's where we are concerned with finding how much area is underneath a curve or a function between two different x values. So this picture here on the right, we've got from 0 to 5, we would want to know how much area is under the curve of that function. And that's called integral calculus. And the way that we do that in general, and we've talked about this a little bit in class, is what we call Riemann sums. And basically, if you were to try and find the area under a linear shape, that would be really simple to do. This shape is a little bit harder to do because you've got all these crazy curves. And so really, we're trying to break it down into pieces that we can find the area of. And that's what a Riemann sum is. Now, before we get too much into that process, just a quick review of sigma summation notation, because this is something that you've got to be familiar with and recognize what this is telling you to do. So when we're finding the areas under the curves, we're going to be adding together, basically we're going to be breaking up the shape under the curve into a bunch of different shapes and then adding them together. One of the ways that this is presented to you is with the sigma, our Greek capital letter. And what it looks like, what it's basically saying, and you should have seen this at some point in Math 3, I'm hoping. It's not really going to be on today's assignment, but it's something you've got to be familiar with. So basically what it's saying is, starting with this value, I'm going to plug that in. And really, if that's an I, this should be an I. I'm going to start plugging that in. So I'm going to say, okay, f of 1. And then I'm going to add the next value up, f of 2. And then I'm going to add the next value up, f of 3. And I'm going to keep going until I get to the top number, f of n. Okay? So putting that into another example, I'm going to start at 1, and I'm going to start plugging it in right here for I. So I'm going to get a 1, and then I'm going to add when I is equal to 2, which just is 2. And then I'm going to add 3, and then 4, and 5, and 6, and 7, and 8. You're going to add all those up together until you get to the top number, 8, and that's where you're going to stop. Okay? So now applying this to a function, if x is -1, if that's where we start, then I'm going to start at 2 times -1. And then I'm going to add the next number up, which is, whoops, let's put the 2 in front, 2 times 0. And then I'm going to add 2 times x for the next number, which is a 1. And then I'm going to add 2 times 2. And then I'm going to add 2 times 3, and I'm going to add 2 times 4, and it tells me to stop when I get to x being 4. But I've got to add all of those together. Okay, same thing down here. As if I start when k equals 0, that's 0 squared, but then I add 1 squared, and then I add 2 squared, and then I add 3 squared, and then I add 4 squared. And I'm going to add all of those together. One way that you can do this on the calculator, you're not going to be doing a lot of this type of summation by hand, but you can do them on the calculator. If you hit alpha and then window, the window button, if you look at the alphas, it takes you to these shortcuts right here. And one of them, yours might just say SUM for summation. Mine actually gives me the sigma symbol, so I'm going to hit enter on that symbol. And what's cool about it on the newer calculators, it gives you the picture. One thing to be careful of, it always wants your variable to be x. So make that an x right there. Even if it's an I or a k or a w, change it to an x. And then it wants to know where you're going to start. So if we do let's do our -1 function. We go from -1, and then you hit the right arrow, and we're going to go up to 4, and then it wants my function, which was 2x. And when I hit enter, it's going to add all of those together for me and tell me that my answer is 18. So if I had added all of these together, I would have got 18. Now, if you have an older calculator, the other way of getting to this, like if you have a TI-83, I believe if we go to stats and it's over in, maybe it's not, oh, where are we at? Stats, calculate, it's not in stats. Is it in distribution? Maybe not. Actually, you know, it's probably not on this calculator. If you are doing this on like a TI-83 or an older TI-84, under the stats menu, I believe, under calculations, you'll see one that says SUM. So you click enter on it, and then you're going to go back into that same menu and find the one that says sequence. Because what you're doing is you're going to sum a sequence of numbers together. And then it's not going to give you this cool notation like my calculator did. It wants you to put the function first. So the same one that we just did, you would put a 2x, comma, then your variable, comma, then your starting point, comma, and then a 4. And then you would close your parentheses. I don't think my version of the calculator will do that just because it doesn't have as many of the functions as yours does because it's still in beta. So this is for the TI-83 or an old TI-84. You do summation, sequence, and then your function, variable, lower bound, upper bound. Hit enter, and it'll do the same work for you, okay? All right, so again, not something that we're going to spend a lot of time on today, but it is something that I think it's important to remind you of because it's been a while. It's been a while since you've done summations. All right, back to calculus. Riemann sums. So it's named after a mathematician. Basically, the important information from all of this that you're looking at is that this is an approximation of the area. It's not the exact area, it's an approximation. And basically what Riemann came up with is because I have this ugly function, I mean, if I had a linear function, which is just a line, right? And I wanted to know, what's the area between 0 and 8? Well, that's not too hard to do because I can just make a parallelogram right here, or a trapezoid, and I know the area of a trapezoid. That's a pretty easy area to find. The problem is most functions aren't that nice. Most functions look a lot messier, and it's some sort of curve, kind of like the examples right here. So what he came up with is if I've got these weird curved functions, and I want to find the area underneath it, I need to break it up into shapes that I can work with. And the easiest one to do is rectangles. So he said, all right, let's just make a bunch of rectangles inside there, and let's find the area of those rectangles and add them all together. And that'll be approximately my area. Now notice the problem. Depending on where you start your rectangles. So this one on the left, this is called a left Riemann sum. And notice that it starts the rectangles on the left side. So when it does that, when you start at that left point and draw this rectangle, you leave out quite a bit of area. But then on the next one, when I start on the left, I actually go up and above the line a little bit, and then I go below it again, and then I go above it. So with this left one, it's a pretty good approximation, but you have all of these areas that you're missing, right? You have all of this space that you didn't calculate, and so it's an underestimate. It's an estimate, it's an approximation, but it's low. If I do a right Riemann sum, then instead of using the left endpoints, I use the right endpoints, which usually make my graph an overestimation because my rectangles end up being bigger than my function. There's also a midpoint. So let's say that this is 0, and let's use something that we can see. Let's say this is 0 and this is 4. So each of these distances is 1. Instead of starting your rectangle at the height of 0, the midpoint says you start at the height of, that would be 0.5. So you start in the middle. So you get a little bit of overestimation and a little bit of underestimation, and hopefully those cancel each other out, right? So right here, you've got a little bit of over, a little bit under, they cancel out. A little bit under, or a little bit over, quite a bit under, and then same thing here. So you get all of these overs and unders that hopefully balance each other out and you get a better approximation. In fact, this is the closest that you get to the true approximation. The trapezoid rule does the same thing, the same idea, but instead of making rectangles, you make trapezoids. And this one gets even more accurate because if you notice, you take instead of just looking at the left endpoint, you consider the left and the right endpoint, and you find the area of this trapezoid. And then you consider the left and the right, and you find the area of this trapezoid. So your values, because both endpoints are actually on the graph, your values are a little bit better. Now, here's the coolest part about this Riemann sum idea, is the more rectangles or trapezoids that I make, the better estimation I get, all right? So, for example, if you look at this graph right here, when it says number of partitions, it's saying if I were to break this up into 2 rectangles, so let's say that we're breaking it up into 2 rectangles. So that means the rectangles are going to start and end about here. But if I do, let's say, a left Riemann sum. So that means my height of my rectangle is going to be based on my left endpoint. So those are going to be my 2 rectangles. And if you notice, there's a lot of area up here. There's a lot of overestimating going on. There's a little bit of underestimating, but there's a whole bunch of overestimating happening. And so if I break it into 2 rectangles, then my left Riemann sum tells me I'll get an area of 36. But if I do a right Riemann sum, so instead of doing a left, if I were to do a right, then I would be, here's my middle again, then I would be estimating here, and I would be estimating here, because I would be using the right endpoints of each of those intervals. And that one gives me an underestimation. My actual value is 29 1/3. It's closer than the left, luckily, but it's still not very close. If I were to do midpoints, then this is the middle of my, come on, pen. This is the middle of my graph, but instead of making my rectangle start here or here, I would start it right in the middle. So I would start my rectangle right here. And then on this one, my rectangle would start right in the middle. So this one, my estimation gets closer. But notice as I break this, instead of just doing like 2 rectangles, the more rectangles I use, the closer I get to 29. If I make this into 4 rectangles, I get down to 32, 28, and 29. If I break this up into 8 rectangles, then I get to 30 1/2, 28 1/2, and 29.25. That's 29 1/4. So just by breaking it up into 8 pieces, I want to be at 29 1/4, or at 29 1/3, and I'm at 1/4. So the more pieces, the more of these little rectangles I make, the closer and closer I get to the actual value. And that's where the calculus comes into play. We are trying to maximize the number of these little rectangles, which we'll do in a couple lessons. So the way that this lesson is going to work, the way that we're going to do this today is we're going to actually draw these Riemann sums, which start with you having to draw the graph, and then you are going to actually create these tables And this is something that you're going to need to do because most of the AP tests I've seen, they don't always ask you, like in this example, we're going to find the right endpoint, we're going to find the left endpoint, the midpoint Riemann sum, and we're going to use the trapezoid rule. It doesn't usually make you find all four, but it is going to ask you to find one. So starting with this first example, it says to consider the function f of x equals x. What would be the area under this function from 0 to 8? And one thing it didn't give us here, and I'm going to add it, is we're going to break it up into 4 pieces. We're going to make n equals 4. So the first thing that I need to do is I need to graph this function. So I'm going to actually graph it in black. So f of x equals x just means that I go up 1 over 1, up 1 over 1, up 1 over 1, up 1, up 1, up 1, up 1, up 1 over 1, right? So my function is going to look something like this. Now I stopped at 8 because look at my interval. It only wants me to go from 0 to 8. So that's where I'm going to stop. I don't care what's happening after 8. I'm going to stop right there at 8. Now, in order to find my right endpoint, Riemann sum, that means that I'm going to break this up into 4 pieces. And each rectangle, each of those 4 rectangles, I'm going to base the height of the rectangle on the right endpoint. Now, what that means is we've got this formula, and I don't like to use the formula because it's another formula to memorize. But the simple way of looking at this is my interval I go from 0 all the way over to 8. But each of my rectangles, I want 4 different rectangles. Well, if I'm going a distance of 8 and I want to break that up into 4 equal rectangles, that means each rectangle is going to be 2 units wide. So one of my rectangles is going to end right here at 2. Then I'm going to end at 4. Then I'm going to end at 6. And then my other rectangle is going to end at 8. So they're equal widths. They're all the same. Now that formula, if you can't problem solve through the width of the whole thing divided by how many you want, the formula is something like this. B minus A over N is going to be your width. And that's if you're using an interval of A to B. So you take B minus A, so that would be 8 minus 0 divided by 4. That gives me 2. So that's my width. Pretty easy to come up with, but that's where it comes from. So I know I'm going to go 2 wide. And so for my right endpoint, my height is going to end at the right endpoint of my function, of each of my intervals. So my 0 to 2, my first rectangle, is going to be at the height of 2. My second rectangle is going to be at the height of 4. My third rectangle is going to be at the height of 6. My fourth rectangle is going to go all the way up to 8. So my rectangle's heights correlate with the right endpoint of the rectangle, where it meets the graph. So really, now I just have to multiply and find the area of each rectangle and add it together. So my first rectangle is 2 wide, and it's 2 tall. So I'm going to do 2 times 2. My second rectangle is also 2 wide, but this one is 4 tall. So I'm going to do 2 times 4. My third rectangle is 2 wide, but it's 6 tall. So I'm going to do plus 2 times 6. And then my last rectangle is 2 wide, but it's 8 tall. So I'm going to do 2 times 2 plus 2 times 4 plus 2 times 6 plus 2 times 8. And hopefully you're recognizing that all of these are the same width. So all of them are going to be multiplied by 2. And really, all I have to do is add the heights together, right? Because all of these are being multiplied by 2, all of these heights. So rather than do all that math, if all the widths are the same, I'm just going to add together the heights. So 2 plus 4 is 6, plus 6 is 12, plus 8 is 20. So this just becomes 2 times 20, which is just 40. So my right endpoint Riemann sum is going to be 40 units squared. I'm okay with that. That sounds about right. So let's get rid of these right endpoints. And we know that's an overestimation, right? Because we went to the right, we were overestimating. Now my left endpoints, I'm still going to break this up into 4 groups. But instead of starting at the right end of my interval, I'm going to start at the left end, which means my first rectangle is at the height of 0. My second rectangle starts at the left endpoint of that interval and goes to the right of the interval, right? So from 2 to 4, I'm going to use the left endpoint. From 4 to 6, I'm going to use the left endpoint. And from 6 to 8, I'm going to use the left endpoint. So just like our overestimation, notice that we've got a lot of area that we're missing. I mean, we're only finding the area of this part of the graph. So we're kind of missing a lot. It's going to be an underestimate, but that's okay. It's just an approximation. So left endpoints, let's add all of these together. Well, the first one is 2 wide, but it's only 0 tall. This one right here. So 2 times 0 plus the second one is 2 wide, and it's 2 tall. So 2 times 2. Plus the third one is 2 wide, but it's 4 tall. And the fourth one is 2 wide, and it's 6 tall. So just like the right endpoint, all of these heights are just being multiplied by 2. So I could write it out this way, or I could just say they're all 2 wide. One of them is 0 tall, one of them is 2 tall, one of them is 4 tall, one of them is 6 tall, which is just 2 times 2 plus 4 plus 6 is 12, which gives me an estimate of 24. So look at how big of a difference that is. My right endpoint is estimating at 40. My left endpoint is estimating at 24. That's a really big difference. So let's try the midpoints. So if I look at oh no, don't do that. We just want to get rid of this green stuff, right? So if I look at the midpoints, so we'll do this one. Let's go ahead and do blue. My interval goes from 0 to 2, which is going to make my midpoint 1. So that's where my height is going to come from. So from 0 to 2, I'm going to go up to 1. From 2 to 4, my midpoint is 3. So that's where the height of my rectangle is going to go. From 4 to 6, my midpoint is 5. So that's where that height's going to go. And from 6 to 8, my midpoint is 7. So that's where that rectangle's height is going to go. So for this one, they're all still 2 wide. Every one of these rectangles is 2 wide. So I'm going to skip the long method, and I'm going to write 2 times, I've just got to add all the heights together. So my first one is 1 tall. My second one is 3 tall. My third one is 5 tall. My fourth one is 7 tall. So that just becomes 2 times 4, 9, 16, which becomes 32. So my midpoint says that I should be at 32 units squared, which happens to be right between 40 and 24, which kind of makes sense because my function's a linear function. It's a straight line. So the right endpoints and the left endpoints, of course, the midpoints is going to be right in the middle. That doesn't always happen, but this is a linear function, so it does kind of happen. Now the trapezoid. This is the fun one. It gives us, the nice thing about the trapezoid is it gives us our best estimate. The bad thing about the trapezoid is it takes the most thought trying to put it together. So here's, let's try and sort through this. So the way the trapezoid works is if my interval goes from 0 to 2, then that's where I'm going to connect those two with a line. And that's what I'm going to find the interval of. I'm going to find the area of that trapezoid. So my next one starts at 2 and ends at 4. So I'm going to connect those dots, and that's going to be the top of my trapezoid. My next one goes from 4 to 6. I'm going to connect those dots. And then my next one goes from 6 to 8. I'm going to connect those and get this function here. So my first one, if you don't remember the area of a trapezoid, remember it's one, and I'm gonna write it this way because technically our trapezoids are tipped over, right? Usually when you see a trapezoid, it's drawn like this, but ours are tipped over. So we take 1/2 and we multiply that by the base, and then we multiply that by, if I take my first height and add my second height. So I'm taking the average of those two heights and then multiplying it by the base. It's been a while since we've done trapezoids. So the nice thing is my base is always the same. So for my first area, I'm going to do 1/2. My base is 2 wide. My height 1 is 0. My height 2 is 2. Then I'm going to add my second trapezoid. So it's 1/2, it's 2 wide. My first height is 2. My second height is 4. Then I'm going to add 1/2 times my base, which is 2. My first height is 4. My second height is 6. And then I'm going to add 1/2. The base is 2. My first height is 6. My second height is 8. So when I simplify all of this, the 1/2s and the 2 just become 1. So basically this becomes 1 times 2 plus 1 times 6 plus 1 times 10 plus 1 times 14. So 2 plus 6 is 8, plus 10 is 18, plus 14 equals 32. So the midpoint and the trapezoid actually gave us the same answer. Again, it's a linear function. I would expect to get the same answer. It's linear. So let's try one that is not linear. And we're probably not going to do all of the Riemann sums, but we'll pick a couple of them. So this function is x cubed minus 4x squared plus 10. This is not a nice function. I mean, if we go ahead and let's look at what it looks like. So we've got x cubed, so x raised to the third, minus 4x squared plus 10. So when I graph this, yeah, that's not a very pretty function. The nice thing is if I'm looking at my graph right here, I don't need the whole function. Look, I'm only going from 0 to 2. So I'm going to go back to my calculator, and I'm going to change my window, and I'm going to make my x minimum 0. I'm going to make my x maximum 2. Nope, 2, please. And then my scale, I'm going to go up by 0.5 because I'll show you why in just a minute. But my y minimum, we're only interested in when we're dealing with the positive. So I'm going to go ahead and set my y to 0. And my y maximum, I don't know, let's make it 20 just in case, because I don't know how big these numbers are going to get. So when I graph this, so there's my function right there. I'm going from, and again, I'm looking at these numbers, and they're not going to be very nice numbers. So one method, I mean, we can graph that. But trying to find like Riemann sums, I mean, look at some of these values right here at 0.5, which is right here. If I go to 0.5, nope, where is 0.5? 0.5 is there. I don't know why it didn't go up the way I said. I'm almost at y equals 9. But if I go to like 1, if I make my x equal to 1, I don't think my numbers are going to be very nice. So, well, I guess I can just hit enter, right? When x equals 1, y equals 7. When x equals 0.5, y equals 9.125. When x equals 1.5, my y is 4.375. They're not nice numbers. But going back to my situation here. I'm going from 0 to 2, and we're going to use n equals 4 again. So that means that my distance, I'm going on my x scale, I'm going from 0, and we're going to ignore these numbers right here, and I'm going up to 2. But I'm splitting it up into 4 pieces. So my distance of 2 is split up into 4, which means that each of my intervals, this is 0.5, this is 1, this is 1.5. I'm only going up by 0.5 this time. So when I'm trying to find these values, these left and right endpoints, let's do the left endpoint first. Okay, I know it says right endpoint first, but let's do the left endpoint first. So my left endpoint for each of these intervals, and I'm making up my rectangles right now, but I just want to see that my left endpoint is going to be based on when my function is equal to 0 for my first one. So my left endpoint is going to be 0.5 wide, but the height of it is going to be f of 0, right? That's how tall it's going to be. When I plug in a 0, what do I get? The height of that rectangle. My second rectangle, and I know these aren't the right numbers. We're just basing this on, I know that the 5 isn't the right number, but my second rectangle is also 0.5 wide, but the height of it, it's at 0.5. So it's going to be at f of 0.5. My third endpoint is going to happen at 1. So it's 0.5 wide, but it's going to happen when f is equal to 1. And my last one is 0.5 wide, and it's going to happen right here, right here, where f is equal to 1.5. So those are the values I'm interested in. I'm interested in when my left point hits the graph. Now I'm going to cheat just a little bit because I know I'm going up by 0.5. So I'm going to go to my graph, and I'm going to go to the table. And instead of all these numbers that it wants to give me, I'm going to make up my own. And I think, let's go down to independent variable ask. So instead of their numbers, I want to know what happens when x is equal to 0. And why is this not working? Does it not work on mine? Is that why it's blacked out? No, I need you to ask me, table. I don't want you to... okay, so maybe it doesn't. So let's just go up by... We're going to start our table at 0, and we're going to go up by 0.5. So I'm just... On yours, you can set the independent to ask, and when you go to the table, you'll be able to plug in your own values. I don't know why this version doesn't let me do it, but the ones I'm interested in, when x is 0, my height is 10. So I'm interested in that one. So f of 0 is equal to 10. F of 0.5 is 9.125. So f of 0.5 is equal to 9.125. F of 1 is equal to 7. F of 1 is equal to 7. F of 1.5 is equal to 4.375, I think. And f of 2 was equal to what? F of 2 is equal to 2. Okay, easy enough. So f of 2, the height is 2. So instead of this fake graph right here, just to give us some sense of where we're at, we're going to call this 1, we're going to call this 1.5, this is going to be 2, this is going to be 0.5, and this will be 0. So at 0, I'm up here at 10. Okay, at 0.5, I'm up at 9.125, which is like right here. At 1, I'm at 7. At 1.5, I'm at 4.375, so just under half. And then at 2, I'm at 2. So my graph looks something like this. I don't know what's going on. But I don't really care because the only thing I care about are these specific values. I only care about those actual values. So for my left endpoints, I need 0.5 times f of 0. So 0.5 times f of 0 was 10, plus 0.5 times f of 0.5, which was 9.125, plus 0.5 times f of 1, which was 7, plus 0.5 times, f of 1.5, which was 4.375. That's a lot of calculation. And you know what? We're not even going to type it in. I don't want to take time on a video for you to watch me type that in a calculator. But remember the shortcut. All of these are 0.5 wide. So you could just do 10 plus 9.125 plus 7 plus 4.375. The important thing is that you recognize the left endpoints where those happen, okay? Because this graph is going to look something like this. Because my endpoints are based on, whoops, that's not right, Mr. Reed. My first one was right. My endpoints are based on the left side of the interval, right? They're based on these left endpoints. That's the height of my rectangle. Now to do my right endpoints, I've got to change all of this. I'm not going to erase my values because I want those. But to do my right endpoints, this time I'm going to look from when I go from 0 to 0.5, I'm interested in this height because I'm going to use my right endpoint. And when I go to 1, I'm interested in that height. And when I go to 1.5, I'm interested in that height. And when I go to 2, I'm interested into the height at 2. I'm interested in the right endpoint. So these are all 0.5 wide. So I'm going to skip the long method. They're all 0.5 wide. The first one is 9.125 tall. The second one is 7 tall. The third one is 4.375 tall. And the fourth one is 2 tall. Not too tall as in it's more tall than it should be, but too tall as in it's 2 units tall, right? So add those all together, multiply them by a half, and it's going to give you the area, which is going to be an underestimate, which is kind of weird because usually the right estimates are over, but because our function's going down, it's actually going to be an underestimation. Now for the midpoints. Again, we'll just write this out really quick so you can see the example. For my midpoints, I don't care about what's happening at 0 and 0.5. I want to know what is happening at 0.25, which we don't know yet because we haven't looked up that value. I also want to know what's happening between 0.5 and 1, which is at 0.75. I also want to know what's happening at 1.25 and what's happening at 1.75. What's happening at those values? I can find out. I can go to my table, and instead of 0 and 0.5, I can put 0 and 0.25 and 0.5 and 0.75. You can find those values. Again, we're not going to take the time to do so. But what's important is that you recognize how we're getting these values, okay? So these are what my rectangles would look like. Some of them are going to be over, some of them are going to be under, just because of the nature of the midpoint. That's what's nice about it, is it takes into consideration what's happening to the left and the right. So you end up with some really nice numbers. So I'm going to take 1/2 the 0.5, and I'm going to times it by all of those heights. I don't know what they are, but I know it's f of 0.25 plus f of 0.75 plus f of 1.25 and plus f of 1.75. If you really want to, you can add those together for me. Tell me in class what that actual value came out to be, okay? All right. So what happens when our intervals are not all the same size? Up to this point, we've made this distance right here the same. We've made the width of our rectangles exactly the same. But sometimes, especially in story problems, those intervals, that increments, they're not always equal. which just means that we can't use this shortcut. You can't do 0.5 times all of those. You have to actually calculate each rectangle separately and then add them together. So for example, concert tickets are sold online. At 12 noon, they go on sale. The chart gives the number of tickets per minute that are being sold at various times. Use a right Riemann sum as well as a trapezoid rule to approximate the total number of tickets sold over the 15-minute interval. Okay, so long story short, here's 0 minutes, here's 15 minutes, which makes this 10 and this 5. So 1, 2, 3, 4, 6, 7, 8, 9, 10, 11, 12, 13, 14. And then it tells me the number of tickets sold. We're going to count up by, let's say this is 100, this is 200, this is 300, this is 4. And you don't have to draw this. I just want you to kind of see what's going on. Because when I look at this table, it tells me the time on the left. Okay, so at 12, so at 0 minutes, there was 150 tickets sold. So at 0 minutes, there was 150 tickets sold. At 1 minute, they're selling an average of 325. So at 1 minute, we're up here at 325. At 12:03, at 3 minutes, which is right here, they're selling 400. So at 3 minutes, we've got 400 right here. At 5 minutes, we're at 425, so a little bit higher. At 8 minutes, we are up to 475. And I know these aren't going to be perfectly to scale, but I'm just trying to show you what's going on. At 12 minutes, we're at 375. So we kind of drop down here to 375 at 12 minutes. And then at 15 minutes, we're selling 250. So these are the average ticket sales per minute at this amount of time. So it wants me to estimate the total tickets sold using a right Riemann sum. Now here's where we got to be a little bit different because my interval is going to change. All right, my interval is not always 1 minute. In fact, my first interval, this one right here at 0, I have 150 tickets. At 1, so here's one right here, I'm up to 325. So from 0 to 1, 1 minute has passed, and I'm using a right Riemann sum. So I want my height to be right there. So there's my rectangle that I'm going to use. Now from 1 o'clock to 3 o'clock, this time 2 minutes has passed. And now I'm up at 400. So here's 3 o'clock, or 3 minutes. I'm up at 400. At 5 minutes, I'm up to 425. Now I'm using my right Riemann sum. So I'm going to the right end of the interval. So this interval ended at 5. The next interval ends at 8. So that's where I'm going to draw my rectangle height. I'm going to draw it at that 8-minute mark. Then I'm going to end at 12 minutes, which is right here. And that's the height that I'm going to use. And then at 15 minutes, I'm going right here. So all of these rectangles, they are not the same width. Okay, this first rectangle right here is 1 by, how tall is it? 325? It's 1 wide, it's 325 tall. My second one is 2 wide, and it's 400 tall. My third rectangle is also 2 wide, but it's 425 tall. My third rectangle is 3 wide. It goes from 5 to 8. And it's also 475 tall. My fifth rectangle goes from 8 to 12. So it's 4 wide, and I'm at 375. And from 12 to 15, that's 3 wide, and I go up 250. So when I add these together, I'm adding all of these rectangles. I'm taking 1 times 325 and adding 2 times 400, and then I'm adding 2 times 425 and adding 3 times 475, plus 4 times 375, plus 3 times 250. And when we add all of those together, I believe we come up with 5,650 tickets sold. All right. So that's my right Riemann sum. I use the right endpoint to make my rectangles. They're not all the same rectangle because it's based on different measurements. Now, if I wanted to do the trapezoid, actually, let's erase all of this green. We'll try really hard not to erase something that we're going to want. Let's just get rid of this green stuff. At least the green stuff up here. Oh, we lost a point, didn't we? That 425 was right here. Okay, so this time, instead of using our Riemann rule, this time we are going to use the trapezoid rule. So what that means is from 0 to 1, I'm going to use the point at 0, and I'm going to use the point at 1, and I'm going to connect those and make a trapezoid. Then I'm going to go from 325 to 400 as I go from 1 to 3. Then I'm going to go from 400 to 425 as I go from 3 to 5, and then 425 to 475 as I go to 8, and then down to 375 at 12, and then down to 250. So these are the trapezoids that I'm trying to find the area of. So the area, remember, it's 1/2 times the base. So how wide is it? That one's 3 wide because I go from 5 to 8. But then I have to times it by the 2 heights added together, 425 plus 475. So that's that trapezoid. My next one is 1/2 times the base. This goes from 8 to 12, so it's 4 wide. And then I'm going to add 475 plus 375. I'm going to add the 2 endpoints of my trapezoid. My last one is 1/2 times 3, and then my endpoints are 375 plus 250. And then these over on the left that I skipped. 1/2 from 3 to 5, that means it's 2 wide, and it goes from 400 to 425. From 1 to 3, that's also 2 wide, and I go from 325 to 400. And my very first one, this one right here, it's 1/2 wide, and it's 1 wide, sorry. It's 1/2 at the beginning because it's a trapezoid. And then I start at 150, and then I go up to 325. So to find this one, I've got to add all of that together. I've got to take 1/2 times 1 times 150 plus 325 and add all of these other trapezoids that I found. I'm not going to write that all out. Again, that's 5 minutes of time you don't need to watch. But once I add all of those trapezoids together, I end up at 5,775 tickets. So one estimate gave me 5,650. The trapezoid gave me 5,775. So that's a pretty big difference if you're talking about numbers of tickets sold. I mean, that's 125 extra tickets. But relatively speaking, those values are roughly pretty close, closer than they would normally be, because the Riemann sum, as we were going up when we were doing the right hand, we were getting a bunch of overestimates. And then as we came back down, we were getting underestimates. So the over and the under kind of canceled each other out a little bit on the Riemann sum, as well as the trapezoid. So one more question. I know this is a long video. It's a lot to cover. And we've got even more that we'll practice in class. But this last one I wanted to show you is a calculus question from the AP test. This is from the 1998 AB test. And we haven't really tied integrals into the Riemann sum yet. But I like this question because I think it gives you a little bit of an idea what's going on. So it's saying that to approximate the integral from 0 to 50, so I know that I'm going from 0 to 50 of the velocity of my velocity function with a Riemann sum. Use the midpoints of 5 subintervals. So n equals 5, and I'm using the midpoints, and it wants them to be equal length. So if this is my data, I'm going from 0 to 50. So I'm going to blow this up a little bit. And I'm breaking it up into 5 equal sections. So if I'm going 50 units and I'm breaking it up into 5 sections, each section is going to be 10 units long. So my first one is I'm going to go right here to 10. And I know I'm zoomed in. I'm going to try not to cover stuff up. But I'm going to go from 0 to 10, and then to 20, and then to 30, and then to 40, and then to 50. So those are my intervals across the bottom. Now, it told me that it wants me to estimate using the midpoints. So I'm not interested in the value at 0 or the value at 10. I'm interested in the value right in the middle at 5. So I'm interested in that value right there. That's going to be my first rectangle. And then I'm not interested in 10 or 20. I'm interested in 15. I'm interested in the value right there in the middle. And then I'm interested in the value at 25. That's the height that I'm going to go to as I go from 20 to 30. And then from 30 to 40, I'm interested in the height at 35. And then from 40 to 50, I'm interested in the height at 45. So these are what my rectangles are going to look like. And it doesn't give me a function. Even better, it gives me this nice table that I get to pull data from. So I was interested in when t was 5, 15, 25, 35, and 45, right? So at 5, my height is 12. So this height is 12. At 15, my height was 30. At 25, my height was 70. At 35, my height is 81. And at 45, my height is 60. So when I write out this summation, and I'm going to go ahead and work up above just a little bit. My first rectangle is 10 wide, and it's 12 tall. And in fact, all of my rectangles are going to be 10 wide. So I'm just going to put the 10 in front, and then I'm going to add the heights together. Or you can do every one individually. That's fine as well. So my first one is 12 tall. My second one is 30 tall. My third one is 70 tall. And then I get up to 81. And then I get up, or I guess I go down to 60. Okay? So 10 times all of that added together, I think becomes 10 times 42, 112, 193, so 253, which means it's at 2,530, is going to be the number of my answer. And I believe it told me to make sure I'm using correct units. Okay. So here's where we need to be careful with our units. This 10 right here represents the width, which is seconds. These values all right here represent the y, the up and the down, which are feet per second. So when I take seconds and I multiply by feet per second, the seconds cancel, and all I'm left with is a distance of feet. So my 2,530 has a unit of feet. So that's the first part. It wanted me to approximate. Well, there's my approximation. Using the midpoints. Using correct units, explain the meaning of this integral. Okay, so we just skipped over what we were even reading about. The graph of the velocity of a car traveling on a straight road. Okay, so the meaning of this integral, that I went 2,530 feet from 0 to 50. So you could say that from 0 to 50 seconds, the car traveled 2,530 feet. Okay, so in 50 seconds, the car, from 0 to 50, the car went 2,530 feet. I would probably word it, in 50 seconds, the car traveled 2,530 feet. Either one of those work. This one, make sure to include the actual interval, that from 0 to 50 seconds, that's how far it went. I think they're both going to get you the right answer. Now, the way that this one was graded, and I think this is kind of cool information. This question is worth 3 points, okay? Your first point, you would have gotten if you used a Riemann sum. Okay, your second point would be for your answer. And your third point would be for your explanation. Now, here's what's cool about that. You get a point just for writing this Riemann sum. Just using that Riemann sum gives you 1 point. If you wrote it correctly and then did bad math and got this part incorrect, the actual answer, you could still get 1 point for writing it correctly. You could also get a point for answering it correctly, even if you didn't explain it very well. You might have explained it wrong. You might have used the wrong units or said that the car traveled this many feet squared. And that's something that happens a lot because some people, because we're finding area, they automatically assume that units are squared. But remember, we're finding the area of whatever our x units on the bottom are multiplied by our y units. So it's not always, the area isn't always unit squared. We're finding the area of these rectangles, but the area of the values that we are finding don't represent area in real life. We're using the area of the graph to find some value in real life. So don't get stuck assuming that your units are going to be squared. Be careful when you're using your units.